Before we start the discussion on finding the shortest distance between a pair of lines, let us take a look at some types of pairs of lines. First, consider a pair of coplanar lines L1 and L2. Two lines lying on the same plane can either be parallel or intersecting. Thus, there are only two possibilities in case of a pair of coplanar lines. They can be either parallel to each other or intersect each other at a point. Now, consider two non-coplanar lines, like lines L1 and L2, lying on different faces of a cuboid. Now we have a number of possibilities. Two non-coplanar lines can be a pair of parallel lines. Two non-coplanar lines can be a pair of intersecting lines. You can also have a pair of non-coplanar lines that are not parallel and still do not intersect each other in space. Two lines that are neither parallel nor intersecting are called skew lines. Note that skew lines are always non-coplanar. Since they are not parallel, they will intersect each other if they lie on the same plane. Observe that intersecting lines meet at a point. Thus, the shortest distance between two intersecting lines is 0. Now, you will learn to find the shortest distance between a pair of skew lines and a pair of parallel lines. Let us start with finding the shortest distance between a pair of skew lines. The shortest distance between two skew lines is the length of the shortest line segment that joins a point on one line to a point on the other line. For skew lines, such a line segment is perpendicular to both the lines. Consider a pair of skew lines L1 and L2, represented by the vector equations as shown. Here, A1 and A2 are the position vectors of points, say M and N, on lines L1 and L2 respectively. Thus, vector Mn is given by vector A2 minus vector A1. Let this be equation 1. Let vector AB represent the shortest distance vector between lines L1 and L2. Let the shortest distance between lines L1 and L2, or the magnitude of vector AB, be d. Thus vector AB is equal to d into unit vector n in the direction of vector AB. By definition, vector AB is perpendicular to both lines L1 and L2. This implies that vector AB is also perpendicular to both the vectors B1 and B2. Thus, unit vector n in the direction of AB is equal to the cross product of vectors B1 and B2 divided by the magnitude of their cross product. Substituting this value of unit vector n in the equation for vector AB, we get equation 2. Let theta be the angle between vectors Mn and AB. Thus, the projection of vector Mn on the shortest distance vector AB is given by equation 3. Cos theta is also given by the dot product of vectors AB and Mn divided by the product of their magnitudes. Let this be equation 4. Substituting the values from equations 1 and 2 in equation 4 and simplifying, we get equation 5. Comparing equations 3 and 5, we get the equation that gives the shortest distance between skew lines L1 and L2. The shortest distance between two skew lines, represented by Cartesian equations, can be calculated by the formula shown here. Now, Let us find the shortest distance between a pair of parallel lines. Consider a pair of parallel lines L1 and L2 represented by the vector equations as shown here. Here, A1 and A2 are the position vectors of points, say P and Q, on lines L1 and L2 respectively. Thus, vector PQ is given by vector A2 minus vector A1. Let this be equation 1. Draw a perpendicular from point P on line L1 that meets line L2 at R. Now, vector PR represents the shortest distance vector between lines L1 and L2. Magnitude D of vector PR is the shortest distance between the lines L1 and L2. Let theta be the angle between vectors PQ and vector B that is parallel to both lines L1 and L2. Thus, by formula, the cross product of vector B and vector PQ is represented by equation 2. Substituting the value of modulus of vector PR in the equation for sin theta, we get equation 3 as shown. Substituting the values from equations 1 and 3 in equation 2, we get equation 4 as shown. Taking the magnitude of the terms on both the sides of equation 4 and simplifying, we find the equation for the shortest distance between parallel lines L1 and L2.